everyone. Where it's close to 11, so let's go ahead and get started. Thank you all for coming. I'm really honored to have the opportunity to introduce Kerstin today to give her talk on unleashing the power of data to drive discovery in earth science. I think many of you already know Kerstin. She's a Daugherty Senior Research Associate at the Lamont Daugherty Earth Observatory at Columbia University. And she's been a pioneer in geoinformatics and in data-driven discovery, so I'm really excited to hear her talk today. Kerstin received her PhD in petrology from Freiburg University. Since that time, she's received numerous awards. I won't go down that list. But recently, she's received a number in geoinformatics from GSA and from AGU. She's held a number of really high-profile leadership roles in organizations and in projects, including EarthCube, AGU, the NSF Advisory Committee for Cyber Infrastructure, and she's also been kind enough to serve on our workshop organizing committee for the 4D workshop that's going to be held at Carnegie headquarters in June, which many of you are involved with. She's also led a number of really important projects, including EarthChem, which I think a lot of people here use that data. I know our group does a lot, and it's been a huge resource for us, so thank you. She's also worked in the Geoinformatics for Geochemistry and in the Interdisciplinary Data Earth Science Alliance. So without further ado, Kerstin, thank you so much for coming, and we're excited to hear what you have to say.
Thank you, and I was told to switch something on here. Okay. Does that have a sound? Okay, great. So, I mean, first of all, thank you, Shauna, for introducing me, and everybody for coming, and specifically for Bob to invite me here. It's a real honor and makes me really nervous to be here and talking to this fantastic crowd. I hope that I have a little bit of an interesting message for you. Usually people react to data more and like falling asleep. I don't want to know about it, but I think the world has changed a bit, and that's sort of my my message that I'm trying to convey is what is happening in the data world. Where are the opportunities, but also where are the challenges in actually making this all happen? A lot of talk is happening about data science, data-driven science. What are the requirements for that? And as you heard, my role in the community has really been to support access to data, to manage the data for the community. I always feel a bit like a service organization. I wanted to give you that perspective as well, to hopefully encourage everybody and inspire people to participate more, because we can't really build the right data systems, the right data infrastructure without the scientists being deeply involved in this. There's a lot of articles, I didn't manage to squeeze that in as well, but this notion of will they come, you know, let's build it, will they come? And I was just last week in Berlin at the Research Data Alliance meeting, and there was a specific workshop organized by the German Science Foundation, who has set up a national council on information infrastructures discussing exactly that topic. They said, we will build it and they will come, and I wasn't sure that really is going to work that well. So to start this off, I wanted to, whoops, and I'm not sure if, oh, just give a very brief.
Data science is a hard thing to define. It's a new topic. It's a fairly new area.
I would define data science as the intersection of traditional computer science, AI, math, statistics, and a number of solution areas.
The broad outline of data science is being able to wrestle with vast amounts of complicated interacting data.
I think about it
Oh, sorry.
in a really holistic way. That means you have to think in terms of how you view data, the particular tools that are important for retaining data. If data doesn't have a home, then it disappears.
So that was the most important message at the end to me. If data doesn't have a home, it will disappear, and then it's no good. So this was a group of high-level computer scientists who actually wrote this report, Realizing the Potential of Data Science, for the National Science Foundation. It just came out, so I encourage you to read this. You see it's April 2018, and it was new. And this is a longer video that goes on for 6-7 minutes, I think. The important message here is that data science is at the heart of the scientific enterprise now, and pushing the advanced. Oops, that's not what I wanted. So the same actually obviously applies for the earth sciences, that data science is becoming a really important leg in the scientific enterprise. The things we have to deal with is the rising tide of observational data, huge observation networks that produce data. But more importantly, there are opportunities in doing advanced data analytics and exploring the data that we've already amassed in new ways and taking new looks at this. And we also can use data and the ability to link data and to integrate them to address more complex and interdisciplinary science questions. Now, the screenshots that I took there from the internet are from different departments, and data science in the earth sciences is becoming a big concern for the educational enterprise as well. And I think that's something to really keep in mind. Some of the universities have really pushed forward on that, and others are lagging behind. But we need to make sure that the new generation has the tools, the expertise to do data science. The National Science Foundation identified actually data and cyber infrastructure as one of the focus areas in their, I think it was in 2012 or 15, this report. And clearly, you know, I think that many of you have heard of the EarthCube activity program within the Science Foundation, trying to actually build a more networked system of data resources and computing resources to drive earth sciences forward. The community is clearly growing and building up, and this is statistics from the last AGU fall meeting, where you can see an enormous increase in the activities of the Earth and Space Science Informatics group. We had an increase of 40% in session proposals, 40% of oral sessions increase. So it really shows what's going on. And to me, the full room in this particular session talking about fair data and repositories, which about 5 years ago, there were always the 5 of us talking, is an indication of you know, a community changing. So just to summarize somehow, you know, there's a big need for data to be openly available and to be well curated, because it helps discovery and advance our knowledge of the Earth systems. But an important aspect, especially for publishers, is that with open data, we can improve the integrity of the scientific and scholarly record. Reproducibility is a term that's all over the place at the moment. More important from the funder side is that we gain efficiencies in research resources if we can better reuse our data. And this, to me, I don't probably have time to talk a lot about this, but another field that I'm really passionate about is actually the sharing of physical samples in the earth sciences, because we're not doing a good job in curating those. It's obviously more challenging and requiring physical space and a different level of curation, but I just wanted to mention this and ask you to keep that in mind. Now, open access to data and other resources is clearly been, you know, on especially the professional society's mind, the funders as well. And AGU just a couple of years ago updated its position statement on data, saying that Earth and space sciences data are a world heritage and need to be properly documented, credited, and preserved. And that will then help future scientists to do better science. And it is this, you know, publicly funded data are a public good that also was supported through the OSTP Office of Science and Technology Policy at the White House in 2013, I think, and has, oops, I think I'm touching this thing too often. And that has led to, you know, the requirement of data management plans at NSF or at NASA and so on. And I just wanted to add again, it also pertains to samples. But making data openly available is not easy, and there are, you know, a lot of challenges attached to that. And there was recently a study by the Belmont Forum, an international effort of funding agencies to support more globally activities that pertain to data management. And it shows that investigators, researchers struggle with data because of the complexity of the data, but the lack of data standards in dealing with data is still big, and finding the relevant existing data. This was actually also a finding of a survey that EarthCube did. The biggest challenge for everybody was to actually find data. And you would kind of not expect that. But so open by itself is not enough. What data needs to be, it needs to be discoverable or findable, accessible, it needs to be intelligible and reusable. And this has led to a whole new paradigm of FAIR. FAIR stands for this: findable, accessible, interoperable, and reusable. A lot is going on in that world, and I'm going to talk about that a little bit more later. So I have in the world of data worn, or I'm still wearing many different hats, and I'm going to touch on some of these. Obviously, EarthChem, the Coalition for Publishing Data in the Earth and Space Sciences, the International Geosample Number, IEDA. Oh, the first one was EarthCube and not EarthChem. Okay. So back to make progress in science, we need to be open and share. Just briefly, you know, this has been my focus over the last 10 years. And what I wanted to show here is my focus has been on the small data. When we think about earth science data, there are the big streaming data from global seismic networks, from satellites, and so on. My focus really has been on this data that are generated in the lab or in the field, on samples or in other small observations, usually resides in spreadsheets and is shared in spreadsheets or in the literature. And that has a whole set of its own challenges because it is very heterogeneous, often not well documented. There are no standards for it, and a culture of not quite sharing data, which is understandable because usually these data are very customized. A lot of effort has gone into customized procedures that optimize the results. So the small data, nevertheless, is really, really useful. And so I've given talks multiple times on, you know, the value of small data, and that we shouldn't be just talking about big data, but there is a big value in it. And I refer you to this paper from Heidorn, Shedding Light on the Dark Data in the Long Tail of Science, which emphasized that, you know, when you put this together, that long tail where there are many, many projects, and even if they don't have the millions of funding that are sitting at the head of a curve that plots basically the volume or the funding for a specific project by the number of projects that you have. You have this long tail of small projects that produce a huge volume of data. And there is really, that's the breeding ground of new ideas and never before attempted science, because nobody was able to gather all these disparate data in an efficient way. And we have ways through the data management now to do that. And I just compare it with a puzzle. You know, everybody is working on small data sets that are all over the place, but when you put it together, you actually see patterns. And that's what I think the EarthChem database, for example, has helped do. The PaleoBio database is another one where paleobio occurrences over the entire Earth time have been gathered into one database that you can now explore and see, you know, when events happened over time and so on. So this report that I mentioned earlier, that Fran Berman and these other computer scientists wrote, made a number of strategic recommendations for advancing data science, clearly, you know, doing data science research in computer sciences and related fields, investing into data science education and training, but also investing into a national data infrastructure. And there's a lot of talk worldwide now about data infrastructures. Just coming back from this Research Data Alliance, I learned about the European Open Science Cloud, the Australian data infrastructure, the Netherlands is doing something. It really is a global effort now, and which poses a whole other set of challenges with respect to bringing these national clouds and data infrastructures together. I wanted to drift off a little bit into looking at infrastructures. It's about 10 years ago that I found a fantastic report written by historians and social scientists on the patterns of infrastructure development. This was actually, and the main author on this was Paul Edwards, who was at the time at the University of Michigan. And I really like to get that perspective from social scientists into, you know, what we're trying to do and why we run into problems sometimes and why things don't work anymore. And, you know, what he said here, I think, is so relevant these days for our whole society that I had to just copy this in, that, you know, it always seems the solution, but it's also a problem that's there because it's indispensable, but it's always unsatisfactory because it lags behind in its maintenance and its updates and so on. And those are really the problems we're seeing with data infrastructure as well. He brings up, you know, the value for society of revolutionary infrastructures, and, you know, there's no doubt that infrastructures have had a profound effect on the nature of human societies. And, you know, you have the example of the Roman water supply system that opened the way for building a large capital in ancient times, the railroad system, which allowed for the first time for people to be easily and fast exchanged and led to the first industrial revolution. The second one was the global electrification. And the last one has been the internet that really opened a whole new world of information and facilitated new kinds of businesses. So infrastructures develop along a pattern, and it usually starts with a phase of what Paul Edwards called system building. There is, you know, a new technology, and somebody takes it as an inventor or, and puts a system in place that serves a local community. And with local, I could also mean, you know, a certain discipline. Let's think about data systems. You know, you build PetDB, you build GeoRock, you build, you know, yet another database, and they all are driven forward by just one person somehow. You know, the wizard who knows it all, who knows the technology, who knows the data, who promotes it out in the community. And when that is somehow successful, there is technology transfer. So, you know, I can just think of MetPetDB saying, oh, that's a great idea. We want a database for metamorphic petrology. And here Rick said, oh, the North American volcano database, you know, we want that too. So there is technology transfer, and it always leads to variations over the design because everybody tries to, you know, make it better, fit for their needs. But that leads to diversification. And so the infrastructure doesn't really easily build. But in the third phase, you come to consolidation, you converge again, and it's happening usually by building gateways, building plugs between the different systems. Oops. And Paul Edwards clearly points out that there are, big challenges in these developments. Something that is really important on these so-called reverse salience, these are issues that simply prevent the infrastructure from moving forward. And I had put, these are actually slides that are 10 years old. I gave that, that talk in 2008 in Australia, where the big reverse salience for us at the time were the data publication culture, how were data made available, missing incentives for generating metadata, and intellectual property issues. And lots of tensions. Who wins? We have competition in this market still. Is it my database? Is it your database? Who gets the data? Who owns it? The community needs to change practices, and that's really difficult to achieve. So we could see over the last 10 years that all this has happened and has held things back and still is holding it back. Just last month, a very similar publication came out by Peter Wittenberg and George Strawn, who is actually the head of the Bureau of Research Data and Information, Birdie, of the National Academies here in Washington, where they came to a very similar pattern that is happening, and basically called what Paul Edwards called growth. They called it creolization. So you have these diverse, the variations on the theme. But then at some point you come into this convergence. And this is, the agents who help this attraction and convergence are international efforts where the community is coming together and trying to make it happen. And one of them he mentions there is this Research Data Alliance that I mentioned already. This has become a really important organization for people in my field. We go twice a year to these meetings and really talk about everything related to data infrastructure, be it technology, be it policy, be it cultural issues, and so on. So, and that's basically relating, just to re-emphasize, as Paul Edwards said, that building these infrastructures is not just about implementing a technology. It's even more so about the social agreements that we have, the organizational changes that need to happen, and the cultural ones, overcoming, established practices, values, and so on. In that respect, in my view, the really important agents in the data world, in the data infrastructure that can make things happen are domain data repositories. What I mean with that is these are repositories with a disciplinary thematic focus. So for example, EarthChem is a repository for the geochemistry world. IRIS holds the data for seismics. There is the Biological Chemical Oceanography Data Management Office, PICODEMO. And so everybody has their defined scope and has the disciplinary expertise. These repositories have disciplinary expertise to ensure that the data are reusable, that they well documented, that you work with the community in defining what makes data trustworthy, what type of information do we need to include with the data about its provenance, about instrument settings, and data reduction procedures, and so on. And so this has been, I think, one of my main missions to ensure that domain repositories get the right credit and the right level of funding as well to fulfill this mission. There's a tendency to send people to more generic repositories, be it an institutional library database. There's Big Figshare or Dryad, which are very generic repositories, and they do not have the ability to look at the data and say, yes, there is fractionation correction included with, so I know how that data was reduced and how it's normalized and so on. So in that respect, I think the domain repositories really increase the value of data by making them, on the one hand, findable and accessible, by applying international data curation standards, but they also make them reusable and interoperable, giving them context, the right level of provenance information. They harmonize them, make them machine readable, and so on. And only that combination of expertise helps grow the value of data. And with that, specifically, the small data can grow substantially when it's integrated into these large collections that can be mined in an easy way, which you can't do if a query to a repository gives you 500 data files back. So IEDA is the Interdisciplinary Earth Data Alliance, and it is the data repository that I'm currently heading. It was actually created by merging a whole suite of data systems that were operated at the Lamont Doherty Earth Observatory into one single facility that has been funded for now 8 years by the National Science Foundation in a shared effort as monies from the ocean sciences, the earth sciences, and the polar sciences. The repositories now have getting close to 1 million files with over 75 terabytes. Most of that data, I mean, the large volume data is marine geophysics. So if I would show that, the geochemistry would probably hardly be visible in a diagram. But we also run this registry for physical samples to bring samples onto the internet, and we now have 4.3 million samples registered there already. And the EarthChem synthesis is now at about 30 million individual values. So it's a substantial resource. And another also very successful synthesis is the global multi-resolution topography that is operated by the Marine Geoscience Data System, an incredible resource that you might have used without knowing when you zoom into maps that are offered in the earth sciences. It's available through web services, so if you operate a map, you can easily do that. The scope for IEDA, its mission is to support investigators. That's specifically the mandate from NSF, helping investigators to share their data and samples, comply with NSF's data policy, and hopefully also other agencies in the future more. And while at the same time adhering to community standards that are being developed. So we operate repositories. These repositories really act for data publication and preservation. We help with the data lifecycle management there, doing some automated quality control, but much manual quality control, actually looking at the files and so on. Important that we do assign DOIs to data that comes in. The data can be held private for certain amounts of time, up to 2 years, depending on what the funding agency allows. So that's our repository service. And then we also have these data products like EarthChem, PetDB, and so on. Visualization tools like GeoMap app, you might have used that possibly. But also a lot of community outreach and training, and on the other hand, integration with the evolving data and cyber infrastructures. I should just mention, if you're attending Goldschmidt conference, we run a workshop this year on data science and geochemistry, so if you're interested, please sign up for that. Just brief view, I mean, lots of use. What is most important, and this is something I should mention on the side here. How do you measure the value and the success of a data repository, right? This is, we've moved away from visits to the website, which are pretty useless, obviously. Number of downloads, yes, okay. But to me, the most important measure would be what's the impact on science? What's the science that has come out of using these resources that should be what convinces the funding agencies to keep these projects going. And so I was talking earlier here with the group, which was really exciting to see how these databases are being used. And we, as the operators of these databases, really need to get feedback from you. How are you using it? What is working? What is not working? But we need to know if it was great and you have a great project, that you can let us know what the publication is that came out of that, and so on. Again, repositories, I basically went there already and said, you know, they're making these user-submitted data sets findable and accessible by us following international standards, having DOIs assigned to the data sets. But another important issue is the link to the literature. So we have had over years bilateral linking with Elsevier, for example. So when you submitted a data set to an IEDA repository, actually a little logo of our facility would show up in the publication, and you could click on that and go straight to the data in our repository. That world is changing because obviously neither the repositories nor the publishers could establish hundreds of bilateral agreements with all these facilities. So through the Research Data Alliance, a new effort has formed that is called SCOLIX, where all the metadata that are registered with DataCite contain the link between the data and the article with the two DOIs. So it's an automatic update of, you know, where the linkages are, where the data from a particular paper are. We don't need to do these bilateral agreements anymore. And so again, the issue of reusability. So we do quality control of data and metadata provenance. And it's ultimately all about trust, right? It's data quality. And I've heard so often, you know, concerns about what's the quality of the data in your database. How do we judge that? You know, it's really up to the community, to the scientists, to help us define what level of information do we need to include in these data sets to make you trust the data and say, okay, I can work with that. Our approach is we're not judging the quality of the data. We just say, give us all the information you need, and then you can use that information to say, I don't like this data. And maybe just the fact that the information is missing would make you eliminate the data from your data set, which also should show to you how important it is to properly document the data sets, because without us getting that information, the data sets really aren't as reusable as they should be. And I included a slide that I also used quite a number of years ago where, you know, the data author just writes the paper and doesn't include enough metadata, and then the poor data manager just they're trying their best to add whatever they can find, but that's not enough, and then the user of the system really gets upset about the quality of the database. This ultimately led me to, in 2007, get together a group of editors from major journals publishing geochemical data, and I know Rick was part of that at the time, where we met, I think, 3 times at AGU meetings and Goldschmidt meetings and so on, and agreed on this policy statement that lays out requirements for the publication of geochemical data. That was published, and everything wonderful, and the editors all said, yes, this is great, but it didn't actually lead very far. That was a big disappointment. But I revived this editors roundtable again in 2014 and was encouraged to expand this across the entire earth sciences, to have a talk between data repositories and the publishers to agree somehow on, how data that are part of publications should be curated and published. This was intended to help the data repositories streamline the acquisition of the data, make it more efficient and more comprehensive, what they get, help authors submit their data by having consistent policies and procedures across the journals, and help journals and funding agencies in addressing all these issues of reproducibility and reusability and so on. It was an effort that was funded by NSF and the Sloan Foundation at the time, and actually led to a statement of commitment that was signed by all the major publishers and data repositories, so that was really good. We developed actually sort of a template for journals to lay out their best practices for data handling. We met a number of times, but again, it didn't get too far. It caused some change, but not enough. Last year now, AGU actually got a grant from the Laura and John Arnold Foundation that takes this COPTIS statement of commitment to the next level of implementation. So we gathered an international and multi-organizational group of people and have been running very successful workshops. One of them actually led, was in November here in Washington, that created a number of activities that are all finishing up in June this year to have recommendations and roadmaps forward laid out. So the important aspects here is to make data repositories FAIR compliant and to make the publishers FAIR compliant. So the important thing is that publishers will align their policies so that there is a similar experience for researchers when they have to submit their data, similar approaches to citation of data, and the most important statement is data are not placed in supplements. So the editors have all agreed. If it's going to happen, we'll see. But once again, the goodwill is there, I would say. So just last week, these new data guidelines for author instructions have been put out as a draft. It's to be approved in June, as I said. And the most important points in these data guidelines are that the data repositories, in order to follow FAIR data principles, must show compliance with international standards for data repositories, which means they need to be certified by organizations such as Core Trust Seal or the Data Seal of Approval. That requires us to go through a self-assessment process that describes our data curation procedures and policies. Clearly, something like DOI registration is a requirement for that. Thoughts of sustainability need to be in that. Also, arrangements for long-term archiving, that the data actually are not going to die when the project or the facility dies. Again, supplements should not be used as an archive for data. Authors should send their data to these trusted repositories and then cite and link the data following these data citation principles. In special cases, there obviously are special cases where data cannot be made available, either because it's too big, or it has privacy issues to it, it has intellectual property rights, and so on. That can be explained in the paper and would be accepted. It was clear that some publishers would not sign this unless that statement was made. So I mentioned this already, the requirements for trusted repositories. You can just see what the requirements are. Now that clearly in the development of infrastructure poses a challenge for us as repositories. We want to, on the one hand, be a trustworthy repository and have the right level of operations and implement these international standards, but funding is always limited. And it's more important, or maybe the same level of importance, that these databases and data repositories serve the sciences, that the utility and scientific impact is given. So that balance is really hard to achieve. And I realize that, that's a challenge that actually exists in the business world as well. You need to comply, and so, the conflicting demands of integration, innovation, that's something that, is hard for us as residents in the academic world to easily solve without really having business people in the room. And I think it shows again that we need to even extend beyond social sciences that are involved in data infrastructure development into the business world to tell us how we can best find sustainable business models. What IEDA did was actually, as I mentioned, the name includes the word alliance, because we were created by merging all these different data systems into one umbrella. The way we've been operating was with a common technical and organizational infrastructure. So we have, one big computer room and server room and system administrator and outreach activities and so on, while we maintain these disciplinary curation interfaces and expertise. So we figured that's actually a model that we could potentially expand on and offer this foundational layer of technical and organizational infrastructure to other data facilities that may not be interested or just don't have the resources to become trustworthy repositories. So we could offer that for the trustworthiness, and the science impact remains because the disciplinary curation remains in place. Oops, I said there twice. We had a grant through EarthCube to try that out, but it has actually not moved too far ahead. We had mineral physics as a new component in the alliance, and I need to talk further with Compress. It's going slow to bring them on board. But we had, what else? It was a couple of others. Oh, the metamorphic petrology database joined, and the National Deep Submergence Facility. But there remain many unresolved issues. It's really hard for all the data facilities to keep their cyber infrastructure, their technology, underlying technology up to date in an environment where we don't get additional funds to rebuild the systems we have. So you become, like infrastructures in general, you become outdated. They're the bumps in the road, that are hard to fix. We do have growing data volumes, and the data become more complex as we're expanding user communities. So that's clearly something that we need to address with additional resources or savings on the other hand. Our staff is sometimes really challenged with learning new technology and solutions besides operating and maintaining systems. And that's a very common problem for data facilities. And we all are pushed to move to cloud platforms, but that's a whole other set of skills that needs to be incorporated into our team. So I leave this as food for some thought. Can we find other collaborations that may help us? I'm particularly interested these days in exploring if a collaboration between these domain repositories and institutional repositories can help because they really have the infrastructure for long-term curation, archiving, preservation. Why can't we just be the face to the community that helps with the disciplinary curation while taking advantage of the local institutional resources? And I mentioned that before, we have the metrics for trustworthiness, but what are the metrics for the scientific impact of the repositories? That is really important. So I want to end up with a topic, I think, that we want to expand on into the future. So FAIR data is wonderful, it's findable, it's reusable, but that doesn't mean that we can use that FAIR data for real data science, for mining data. So I think we need to move beyond FAIR to something like FAIR Plus, where the data become mineable, that they are more highly integrated, that they're accessible at a way smaller level of granularity. And I'm again referring to EarthChem, where you can get each individual value is searchable, has its metadata. Samples are a level of data integration or data access that we need to pursue. But that brings a whole set of new challenges, basically, in the data models that we need to use in the adoption of persistent identifiers and metadata that apply fairly broadly. But again, thinking back of this diagram of creolization and then convergence, I'm just starting a project with biologists in developing data models for sample-based data that could be used across different communities. And I think those are the steps that we're taking now to get into these more granular data access levels in a consistent manner. This is just an image from our IEDA data browser showing, more granular access at the sample level or at a cruise level. And, those of you who have used EarthChem know this is basically fusion, data fusion, as compared to, the FAIR data. And we can demonstrate that really the impact on science comes from these fused databases, from the much more highly integrated databases. It's so far I haven't seen the groundbreaking science coming from repositories necessarily, from many data files to be analyzed. So just at the end, very end, a few words about samples. I couldn't resist it. So open samples obviously are necessary for many different reasons. It's reproducibility and reuse as well, and samples are in many cases absolutely irreplaceable with really high value. So the first step that we can take is to introduce the digital sample curation, registering samples, sharing information about samples so they become accessible. There are many other questions that are still open, but that's for the next workshops to solve, I think. So the International Geosample Number basically has introduced the concept of sample registration into a global network of now 24 members. And actually right now we have 6 different places where samples can be registered worldwide, 2 in Germany, 2 in Australia, 1 in Korea, and 1 in the US here. And that helps basically samples become findable on the internet, accessible, even though we don't have policies yet. How accessible does a sample need to be if you have data in a publication? Does the sample need to be shared with the community or not? And samples are now identified in a unique and persistent way, so you can all refer to the same sample with the same identifier. I'm going to skip that and hope that you all are going to answer that question now in the right way or not ask that question at all anymore and say yes, I expect you to share your data, and I think you can get credit for that, and you can get benefits out of it in that accessing data from the whole community helps you and others, but you are part of this infrastructure and need to contribute to it. So just to summarize, I think data-driven science in the earth sciences can only happen if we go beyond open. The value of data and samples grows by making them fair. Domain data facilities play an essential role because they can ensure the quality of data for trusted reuse and also help with community engagement. I do think that we have to pursue more partnerships and collaborations among the data facilities to have more consistent protocols and policies, but also to make operations more streamlined and explore some economies of scale. That's our big challenge in sustainability, because most of us are funded through 5-year grants, and that is not what really builds an infrastructure. So with that, thank you very much, and I hope to get some feedback and comments, and whatever you want to tell me, you can also send me an email. Thank you.
Thank you very much for that talk. So does anyone have any questions?
So in the end, you talked about the open sample, but right now museums don't play this role for sample. How do you see that integrated into existing
Well,
role?
I think we need, I mean, there are obviously institutional collections as well. Lamont has its collections and others. And there are a few sample repositories funded by funding agencies. NSF maintains marine core repositories. There is the US Polar Rock Repository. NASA has the astromaterials collections and so on. So I think that there are ways to actually work between the academic community and the museums. I've had a number of talks with Liz Cottrell from the Smithsonian and so on. They have their own policies, which makes it difficult, but I think that we can learn from them, and they could actually help us as well to, leverage the resources that are out there. It will be difficult. I think, it's interesting when you think of data. Institutions, universities have taken fairly active, play an active role in taking care of data. They build their local, institutional data repositories in the libraries and so on. So why aren't they taking the responsibility for the samples as well? Now, the biggest challenge, I think, is that everybody says, oh, we can't keep everything. And that's true. We can't keep every sample ever collected, but we can make informed choices. And I think that's it's actually a workshop that I've planned for this year still, is to talk about what are the criteria to preserve a sample. I think if you publish data about that sample, that might be, a criteria. If it's well documented and registered, it has a higher chance of being preserved than something that sits in a box in the basement. So I think there are ways we can move forward and work with the museums for the long-term preservation. Yeah, Eric.
One of the things I've always been encouraged about in your approach is the ability to assign DOIs to data sets that are citable in the literature, because all of us know that literature citations have become, in a way, a sort of a coin of the realm, right? And so on the side from journal editors, we're kind of stuck in publications in this printout, the printed sort of paradigm where you have a limited number of citations that you're allowed to include in a scientific publication. And obviously, I think that the citation lists could benefit from an electronic approach like this. Has there been any sort of a progress with the editors to make reference lists be electronic in their nature, so that you're not limited to 50 citations or whatever.
There's a lot of talk going on in the publisher community at these conferences. I forget all these acronyms but they're thinking very heavily. They're thinking of different ways of actually enriching the metadata of a publication DOI with the DOIs of the data in it, or other types of citations, because now there's also the software coming on. We are already at IEDA in the EarthChem library. We're including the IGSNs of a data set in the metadata of the DOI. So there is rich potential to create a much more networked environment of information. So they're really thinking about it. They're thinking about having actually a specific section for data citations or software citations and all these. I think there's the feeling that the paper prints are dying at some point, right? And that just staying within the world of electronic publishing, you can do a lot more. And because it can be integrated with the metadata of a publication or the metadata of a DOI, the space doesn't really play a major role, right? Yeah. Yeah, yeah, yeah.
You brought up the issue of sustainability, but you didn't touch much on the economics of that, in the sense that the service that the data repositories are providing used to be the grounds of the journals, both society journals and professional journals. So for Elsevier, not allowing data in papers or in supplements transfers the cost of maintaining that from the journal to you. So this is a great thing that you've done for the journals, and I'm sure Elsevier is happy in increasing their profit margin. But there has to be some way to get the economics of that back into the data repositories.
No, we're talking about that, the charges for data deposition. Now, I mean, I was actually 2 months ago at a workshop here in Washington on sustainability of data repositories that NSF had called. And lots of talk about business models and value propositions, right? And the business models go into the world of deposition fees that, NSF would rather like to give money to each grant and the investigators, including, $1,000 for data deposition that then comes back to us, rather than funding infrastructure for the data. That seems to be fairly clear. And that could, connect with the publishing world as well. But I've just recently now heard, again, Elsevier coming up with their own ideas how they could make money with data. So I'm not sure what we have achieved here with Coptis and so on is actually going to last if they see that the data, being a repository or so on, it could also give them profit. So it's still, a lot of discussion, and I'm always worried, obviously, because I have 15 people to support. But what are the costs for depositing? With $1,000 and I get 100 data sets in the EarthChem library, I can't survive, right? That's also not an option. It's a very tough question to solve. I think worldwide the funding agencies struggle with it. I think Europe is more, and specifically Australia actually, are more willing to make this permanent infrastructure built directly by the government.
So I'd like to follow up on that funding question. And first of all, I want to thank you for the talk. And really thank you for the contribution that you've made to the earth sciences. We wouldn't be where we are today. And I know how much of a struggle it's been, an ongoing struggle to raise funds. And I'm wondering, when you start talking about not just FAIR, but beyond FAIR, it strikes me that we may be able to use a different rhetorical device. We talk about data repositories or archives or library, and there's this kind of sense in the back, maybe this is kind of it's the dust, yeah. But what I would like to propose would be unfair is we think of this as being, you're building an instrument, you're building a scientific instrument for discovery, when the data is collected together, and if it's interoperable and it's in a format with the analytical and visualization power that's now can be brought to bear, you're really talking about open access scientific instrument for discovery. And I think we need to start using that rhetoric rather than repository or archive. Building an instrument. You know, NSF puts millions of dollars into analytical apparatus and for oceanographic vessels and drilling and things like that. They should put millions of dollars into building other kinds of instruments that are based on...
Which is the next generation somehow. No, I mean, absolutely. The data need to be considered as such. It does bring up always, I mean, if you have an instrument that's shared in the community, you pay for use to a certain point. And this was another sort of business model that was brought up in this workshop. They actually had like 3 case studies of major repositories, are subscription models, right? That you go and your institution needs to sign up for EarthChem, and that's sort of the value added, because what the repositories fulfill NSF's mandate for open access. The data are there, they document it, they're available, you can go there. If that extra effort goes in to take the data, fuse them in one of these databases, that's, another product that maybe people, when they want to use it, need to pay for. So that's just another thought direction that they're taking. Also not so good, I think, for our science, because we've always talked about democratizing our science by providing these instruments. But resources are limited, right, at the moment, especially so.
One of the new things line for earth scientists to deal with are these data journals. You've got a data journal, it's out there, you can put your data, it's citable, it's going to have a DOI. You didn't really talk about how it fits in the structure or in your thinking here. It strikes me as being a more formal type of a supplement. Do you view it as the solution, or do you think it's a more kind of a formal type of thing like a supplement?
No, I mean, it is in most journals, let's say data journals. They work just like these other publications. So when you go to Nature Scientific Data, it's a paper that describes the data, the making of the data, and the procedures that were applied to reduce or compile or clean and so on. But the data goes to a repository. So for example, EarthChem is a recommended repository for Nature Scientific Data. There is, and I know that the Mineralogical Society is currently and I've written a message to Alex Spear already saying, you can't do that. That's not, to have a journal where the data sits just in the paper. Shouldn't happen. So we should have more of a discussion, hopefully, this afternoon about that.
I think we can definitely have time for at least one more.
We address bias
It's kind of funny that that bias exists, because the most impactful papers, I think, in the history of earth sciences have been large compilations of these, what were they called, synthesis papers or review papers, right? So the reuse of existing information has always happened, and maybe actually, I very much appreciated your idea this morning. Let's just gather all the prominent cases of major science that has come out through reuse of existing information. I think, one of the big problems with trying to analyze again. I mean, obviously, new methods come up, better precision. That's when we actually do need to, invest into new methods and so on. But the lack of reuse or the mistrust about reusing existing data is because people aren't sure about the quality, if there is bias in, and it needs to be very transparent in what you do with the data. And again, a better quality documentation and the standards that we're trying to enforce through, the submission to repositories to actually look, is there, all those bits and pieces about precision and how many times the standard was measured and so on. That could help, eliminate the mistrust of science coming out of reused data. I'm not sure if I...
I don't mean necessarily that. I mean, on a much smaller scale, if Rick publishes a data set and I publish a different interpretation of that, my paper is, less valuable to the scientific community and to maybe the tenure committee because I didn't actually collect that.
I see. Ooh, that's a tough one. That's a culture issue that I don't have I don't have a solution or a thought on that. I think it's a great topic to actually look into and maybe see. In the context of these evolving data infrastructures, how much such a paper where you reinterpret and you find new meaning in a data set can actually enrich what's out there, right? We were talking earlier again in this discussion about, the reuse and how currently the group that Bob is working with is kind of putting new information or cleaning information about particular data. And it in some way really enriches what we have, because suddenly there is much better metadata. There is metadata that presents a new perspective on the data, but it doesn't flow back into the data systems, right, which I consider a loss for us. It would be so much more useful if it actually gets attached to whatever data set you downloaded from EarthCube before, from EarthChem. So I think I'm glad you mentioned that, because it's something I haven't thought about and would love to help address.
Value we're adding by synthesizing this information is a conversation we should be having with repositories and how can we incorporate that information. Yeah. Otherwise, it's the same issue, right? It's being lost.
It's being lost again.
Yeah. Okay, so I think I have time for one more.
I started doing this what you're doing in about 1980 in NOAA and did it for 20 years. I came here hoping to see that there's a lot of progress made since I retired 18 years ago. And there hasn't been a lot of progress, and it's depressing. The main thing, I think, is the data and the publications, and I participated in that AGU group a little bit with Rick. But we did everything. We started in NOAA. We started with, I've worked where we had the data centers and the satellite data, and then we went interagency, and we went to the Academy of Sciences committees. We went international with data, space data, or satellite data, and geospatial data. And all the words that you said here, we were saying, I was saying, in like 1985, 1990, and 1995, and it's the same thing over and over again. And the money issue is still the same money issue. So it's pretty depressing to me to see that, and it's like, the main thing I can see is like fighting through molasses. You try to push through, you just can't get anywhere. And
I have to say, we few disappointing when I looked at that talk from 2008. We're still not very far along. It's kind of 10 years already, and we said at that time, because NSF wanted to build cyber infrastructure right away, and this report on infrastructure building said, no, it's not happening fast. It takes decades. And here we are a decade later, and
it's an uphill battle, but it's one worth fighting, so we all have to keep fighting.
Yeah, it's the next generation anyway.
So let's thank Kerstin again. And she'll be around for lunch if anyone wants to chat with her. So.